will mention that at least for the compaction track, one of the ideas is that the process that builds the core is also expected to feed the black hole, and which may presumably lead to quiescence. Okay, so that's one picture of how you might be able to get quiescence. So, if in that case, then we're back to this plot, the sigma 1 versus Mstar diagram, color-coded by the SSFR gradient. If this is the case, and these are the ones that are going through some sort of compaction event, and they're supposedly feeding the AGN, then I would expect AGN to be more prevalent in the upper part of the diagram. So we decided to test this by cross-correlating all the galaxies in Sloan with the WISE survey. And we did an infrared selection of AGN and plotted this plot color-coded by the AGN fraction. And voila. This is the same diagram, only star-forming isolated galaxies. And this is color-coded now by the AGN fraction as detected in WISE. And the blue means higher fraction. So as you can see, the AGN fraction peaks above the line. We've only talked about star-forming galaxies, but I put the contours of the quiescent galaxies on top, just so you can see, for reference, that the AGN fraction roughly even coincides with where the quenched galaxies are. So this is kind of tantalizing picture of perhaps maybe the AGN might be about to quench these star-forming galaxies. So this is kind of a suggestive picture. Well, so then we thought, okay, well, if the AGN are here, and if they are about to quench these galaxies, well, how are they quenching them? So we decided to look at the outflows. If they are about to quench them, we'd expect the outflows to also be prevalent in the upper part of the diagram. So let's take a look. So how did we measure outflows? So what we did was we took the sodium deabsorption doublet. So this is a spectrum. The black is a real data, real spectrum, and the red line is a fit to the stellar part of the spectrum. So I've only zoomed in on the sodium region, but you can do full spectral fitting on the full spectrum for the full range. And what you get is a fit to the stars that looks like this. This is an emission line, the helium line. But the residual has this doublet that's shifted over to the blue part of the spectrum. And this is an indication of an outflow, because if it's an absorption, you know it's in front of the galaxy. And if it's blue shifted, then that means it must be an outflow if it's in front of the galaxy. So that's one of the advantages to studying winds in sodium D, because it's an absorption, you know which direction it's going. Okay, but in order to do this kind of analysis, you need to have high signal to noise. So what we decided to do was to take this diagram, divide it up into a grid, and stack the spectra of the Sloan galaxies in each of the grid cells, and fit the sodium D lines, and see what you get. And this is the result of that exercise. So we measured the equivalent width of the sodium D excess, so the extra sodium D absorption that you need in order to fit the spectrum. And what you see is that the sodium D equivalent width is higher in the higher part of the plot. So galaxies with denser cores tend to have more prevalent winds or outflows. We did also check the velocities. I won't show that plot right now, but we did check the velocities. They tend to be about between 100 and 150 kilometers per second blueward. So there is some second-order dependence on stellar mass. But I'm going to say, which doesn't quite match up with the AGN fraction, and we're still thinking about some of these issues. We're also thinking about issues of inclination, which are very important in these kinds of analysis. So stay tuned for more results in this regard. But I wanted to show you this preliminary result that if you take fixed mass, you're more likely to have outflowing winds if you have a denser core. So this is all consistent with a picture of these galaxies going through some sort of compaction event. Okay, so far, galaxies with compact cores we have seen have centrally peak star formation rate, and younger ages in their centers. They also have higher AGN fraction, and they have a higher prevalence of outflows. Okay, so I have been interpreting this up till now as compaction at redshift 0. So inflows lead to high sigma 1, feeds the AGN, drives the outflows, and perhaps even eventually quenches the galaxy, even though I haven't talked about quenching here. But there's also other possibilities. For example, maybe the sigma 1 of the galaxy was around for ages. Maybe they built their sigma 1 long, long time ago, and because they have high sigma 1, they somehow have a higher probability of having centrally peaked star formation rate and AGNs and outflows. So the causality here hasn't been established. So we decided to ask, well, so what are these galaxies doing? If we see these galaxies at redshift 0, what was their recent history? Did they undergo some sort of compaction or not? So in order to answer this, we looked in the Illustris TNG. So here I have the same diagram I showed you before, sigma 1 Mstar, and we wanted to see if this could be reproduced in Illustris TNG. So all of this work in Illustris was done by my collaborator, Dan Walters, who is not a student. He is actually a pilot who is very enthusiastic about astronomy and wanted to do an astronomy project. So there you go. So Dan went to the public TNG data, downloaded them, and plotted the sigma 1 versus Mstar diagram at redshift 0 for isolated galaxies. So he has some criterion for isolation, and for star-forming galaxies. So star-forming isolated galaxies. And this is they're color-coded by the gradient of the SFR. And what he finds is very similar to what we find in manga. That the galaxies that are above the line, so that first of all, the relation is very close. It's a little bit offset, but it's very close. That this black line is the same as this black line. And so what he finds is the same thing. So galaxies with denser cores tend to have star formation in their centers rather than their outskirts. And galaxies that have diffuse cores tend to have their star formation in their outsides. So there is a little plume of these really dense galaxies. They represent about a few percent of the population, which we don't see in the observations. But since they are a few percent, I'm not going to discuss them here. So Dan went, it's a simulation, so you can follow the galaxies. So what he did, first of all, was he created this movie of the same diagram, sigma 1 versus Mstar, colored by the SFR gradient. And he made a movie that goes from 5 gigayears ago to today, just to see the recent history of this diagram. And what you should see as the movie goes on is that the picture stays the same over 5 gigayears. So the SFR gradients tell the same story. Compact cores have centrally peaked star formation, and diffuse cores have SFR in their outskirts. Okay, so it'll just scroll through again, but it's basically the same picture. So then what he did was he followed individual galaxies. So there's a lot of galaxies here, so he selected a few random ones. And this plot, he shows the trajectory of individual galaxies that ended up above the line. So they ended up having dense cores. And he wanted to see what was their history up until 5 gigayears ago, till today. And this is their evolution. So a lot of them do have these steeper tracks in sigma 1 Mstar. These are the galaxies that end up kind of right in the middle of the relation. And their trajectories are more or less following the relation. Okay, yes, okay. And then these are the galaxies that end up substantially below the relation, and they end up having trajectories that are flat or even negative, meaning they decrease their sigma 1. So he summarized all of these trajectories by plotting the histogram of the slopes of the trajectories. So what he did was he took the slope from 5 gigayears to today, just that trajectory in sigma 1 Mstar, that slope, and he plotted the histogram of those slopes. The pink, and I realized later on that these colors should have been, they're kind of mismatched. Blue here is actually pink, and blue here is actually red. So basically, the pink histogram represents galaxies with compact cores, the ones that are above the relation, and the blue are those below, so with a range. And the line here is the slope of the relation, the main relation. So what you can see is that galaxies that are above the relation, those with compact cores, tend to have steeper trajectories of evolution, whereas galaxies below the relation tend to have shallower relations. Some of them are even quite negative, which means they're losing mass in their centers. And that is probably due to things like stellar mass loss after stellar death. So in summary, what we have seen in the observations is that galaxies with compact cores have centrally peaked star formation in younger ages in the centers. They have higher AGN fraction, higher prevalence of outflows. We interpreted these properties as pointing to a compaction-like track even at redshift 0. And we showed what we're seeing in hydrodynamical simulation, at least in TNG, is that compact cores, we've repeated this observation, galaxies with compact cores have centrally peaked star formation. So we've confirmed that, that hydrodynamical simulations at least predict this. And we've also seen that the current position in the sigma-1 Mstar diagram tells you how the galaxy evolved structurally. So galaxies with compact cores increase their core density recently, which is a sign of kind of a redshift 0 compaction-like process, whereas galaxies with diffuse cores have not grown their cores much over the last 5 gigayears, and even some of them decreased their mass. So thank you very much.
Okay, let's hear questions for Joanna. I like to always start with students first. Right here.
Can you explain how this compaction is actually taking place? So you said that it's happening to get
So, yeah, very good question. So yes, that is one thing that, so I forgot to mention that our future work that we're still working on right now is actually discovering what it is that's causing these galaxies to increase their core mass so quickly. And so we actually looked at mergers, and I'll show you the picture here. Mergers, okay, this is a little hard to see, but Dan has marked in these plots a little diamond everywhere there's a merger, and there's hardly any in this plot at all. These are selected to be isolated, and they hardly have any mergers. So mergers don't really explain much.
Mauro?
I used to be a student.
Yeah.
Joanna, it's a very impressive analysis. My question is, how did you select your AGN? Are these X-ray AGN? Have you tried to select AGN by infrared, hot dust?
So you mean the plot about the observations. This is a selection based on WISE colors. So I mean, various people use different cuts, but it's W1 minus W2 of like the equal to something like, I think it was 0.6 was the border between AGN or not.
Okay, one more. Kameshwar.
So regarding the same wise selection, so I know there's some slight debate in terms of star formation and the AGN simultaneously
Yes.
happening, especially in these like dust obscures sort of systems. So does that affect your results in terms of the AGN fraction being high if you were to consider both star formation and a large amount of star formation and AGN simultaneously?
So we did select in terms of dusty galaxies, we tried to select, we have an inclination cut to make sure that dust effects were minimal. Maybe the inclination cut was a little on the liberal side, but in order to get more numbers. But I don't believe that I can't think of any reason, and maybe you can think of any reason why the selection would be different for galaxies with high sigma-1 versus low sigma-1. Like why one set would be dustier than the other. I haven't seen it in Balmer depth increments or anything like that.
Okay, let's thank Joanna again.